Now, this application of derivative is people a very important part in differentiation, and in most of the areas, in the sense, especially in maths, anyway, we use this application of derivatives, and some other sectors like economics, medicine, physics, and agriculture. In many areas, people, this application of derivatives is used. So therefore, it is very important to us, because in our examination, our question consists of 3 parts. Of the 3 parts, second 2 parts coming from this application of derivatives. Okay, so therefore it's very important to learn this application of derivatives. Okay, first I'm going to discuss the gradient and intercept of a straight line. Okay, now I'm going to consider, the standard equation. If I consider this way, an equation y equals 2x plus 3, people, this equation represents a straight line. If we draw the straight line, we can draw the straight line on the xy plane, x-axis and y-axis. This xy plane, when we draw this line, the line really coming like this. You can draw this line by constructing a small table including some xi to n, finding corresponding y values n, marking those points on the xy plane and joining those points by a smooth line, we get this line. There, people, this x coefficient, this we call it as the gradient, and this is called as the intercept. Gradient and the intercept. The way of defining the people gradient is this. Now see here, the line makes with the positive x-axis. This is the positive x-axis. This line makes with the positive x-axis in anti-clockwise sense. Here, this angle. The line makes an angle with the positive x-axis in anti-clockwise. That angle we can find tan value. For this angle, we can find tan value, tan theta. This tan theta is the way of defining this gradient. To denote the gradient, we usually use the letter simple m for the intercept c. That is how we get our standard equation of the straight line like this: y equals mx plus c. Okay, this is the origin. Now the distance from this origin to the point where the line cuts the y-axis, there is a particular height. This height only, people, we define as the intercept. We define as the intercept. Okay, right, people, to my area now at the moment, raining and lighting also occurring. Sometimes due to this bad weather, we can't smoothly continue the class. If so, if we find a particular risk, today I stop the class in the middle. Okay, if not, we'll continue as usual. If you are unable to do the class today, people will take an extra class. Okay, at the moment, lighting and raining available at the moment, right? So sometimes the internet, of course, strength also become poor under the rainy days. Let's see, people, until something happens, we'll continue. No, yeah, right. Now the intercept is defined. The distance from the origin to the point where the line cuts the y-axis. This one is the intercept, right? So that's the meaning of gradient and intercept of a straight line. The standard equation of the straight line is y equals mx plus c. This m is tan theta. Theta is the angle the line makes with the positive x-axis in anticlockwise sense. Right. Now people will see what is the meaning of this gradient. What is the meaning of this gradient? Right. And when the gradient is positive and negative, the way of drawing the line or the way this line looks like. People, you know, when this angle theta is acute, less than 90, you know, when the angle is less than 90, that angle lies in the first quadrant, no? Angle lies in the first quadrant. When theta less than 90, greater than 0, you know, tan theta becomes positive. That means gradient become positive. Gradient become positive. Then if the gradient is positive, people, this line makes an acute angle with the positive x-axis in anticlockwise. Now, if the angle greater than 90 but less than 5, that means angle in the second quadrant, like this. You know, in the second quadrant, angles, the tan become negative. Then tan theta, right, less than 0, m less than 0. So therefore, when the gradient is positive, the line looks like this way. This angle is an acute angle, right? When the gradient is negative, this theta should be obtuse, more than 90. Therefore, line should be like this. Okay. But remember, people, always when we need to measure the gradient of a line, we have to take the angle with the positive x-axis measured in anticlockwise until the line. This angle only we have to always take to take the gradient of the line. Then in this line, the gradient going to be, people, m equals tan alpha. Since this alpha is more than 90, the tan alpha is negative, therefore gradient is negative. So therefore you have to understand first the straight lines with positive gradient like this, negative gradient like this. Right. People, now if this gradient increases, if this m equals tan theta, no? If this m increases with positive values, the tan theta must increase. For this tan theta to increase, people, the theta must increase. So therefore, if the gradient of the line increases through positive values, this angle should increase. So therefore, if I need to draw some straight lines having or increasing the gradient, as the gradient increases, people, this angle the line makes with the positive x-axis in anticlockwise increases. Right? The other thing is, now if I take this angle as beta, you can very clearly understand alpha plus beta is 180. Alpha plus beta is 180. Then I can, people, subject this alpha, taking this beta to right hand side, 180 minus beta. Then the gradient of this line is tan alpha. M equals tan alpha. M is tan alpha. But alpha is 180 minus beta. Alpha is 180 minus beta. But you know, people, tan 180 minus beta is minus tan beta. Then of course, if we know the gradient of the line is negative, okay, put in there. Now if this shape is the shape of the line, people, obviously we know gradient is negative. Then putting minus sign to measure the gradient, you can take this angle here on the right hand side here. You can take this angle. Taking this angle and its tan we take, put in minus sign before them to get the gradient. So therefore, we can get a single rule there. If you know the gradient of the line is negative, that's a obvious fact, no? If that angle is more than 90 with the first two x-axis in anticlockwise, it makes more than 90, gradient is negative, people. Okay. Then if you know the gradient is negative, putting minus sign for the gradient, you can take the tan of this left hand side angle. Right. Now, there when we further analyze the situation, you can see, now this one I am talking, m equals minus tan beta. Right. Now, people, in this case, you can see, if this angle beta, this angle beta, suppose I'm going to increase like this. I'm going to increase the beta. I'm going to increase the beta. Now, what happened to this gradient, people? You know, gradient is given by minus tan beta, no? M is minus tan beta. Right. When the angle, people, increases like this, this angle is the angle now beta. When it increases, people, you know, this tan beta increases. Right. So, but before that we have minus sign, no? Then suppose initially the angle is beta is very small value, then tan beta we get very small value. Right. Then we get m equals minus, suppose 1. Then secondly, when we bring this beta to a higher value with minus sign, we get greater value, because as angle increases, tan increases, no? So then next one, like this one we get. Then you can very clearly see, people, in this case, when this angle increases, having minus sign, this number value increases. Then the overall value, what can you say, people? With the minus sign, overall value decreasing. Why? On the number line, if I consider 0 here, minus 3 is somewhere here, minus 2 is somewhere here, minus 1 is somewhere here. Right? So then you can very clearly see, when the angle, people, this way increases. Okay. The angle increases. You can see here, for a small angle, minus 1, another greater angle like this we get. Okay. So therefore, remember, you have to remember like this, if the angle this way increase in, people, okay, the gradient is, people, here decreasing. Minus 1, minus 2, minus 3 means decreasing. Okay. And with the gradient positive, people, when the angle is increasing, what happens? Since there is no minus sign before that, like this, the gradient is increasing through positive values. Okay. So therefore, negative gradient line takes the form this. To get its gradient, people, since we know its gradient is negative because of its this shape, right? Put minus sign, and instead of this angle, we can take this angle to get the gradient. Okay. Tan of this angle, put in minus sign before that. Okay. Right. Now this way we can find the gradient. Now let's see, people, the gradient, its real meaning of the gradient. I'll take the like this. Here, x-axis, y-axis, I draw a right angle triangle here, this way. Okay, then here, this angle also theta, because corresponding angle. This is 90. Now you can see, if we take this gap is x and this gap of the height as y, people, you can write tan theta. It is the gradient, no? Gradient equals tan theta equals y upon x. What do you mean by this y upon x? If I give two values for this x and y, x is 2 and y is suppose 3, then here we get y is 3, x is 2. When you divide 3 by 2, we get 1.5. Then the denominator is 1. People, this is the answer. The gradient 1.5. 1.5 divided by 1, that is 1.5. Then what do you mean by this gradient? People, then gradient is this. What is this denominator? It is x. When x changes by 1 unit, the corresponding change in y is the gradient. Is the gradient. When x changes by 1 unit, people, that change of x can occur in two directions. Increasing x by 1 unit, the change can occur, or decreasing x by 1 unit, the change can occur. Anyway, people, suppose we consider the change of x increasing. By increasing this x, suppose its changes occurs. Then when x increases by 1 unit, the corresponding increment in y is defined as, people, the gradient. People, something like this, which is expressed as a fraction, and when its denominator is 1, then that fractional value is defined as, people, rate. Okay, rate. Now, for example, in people, 10 seconds, a child can eat 500 grams of rice. Right? Now, people, we need to find in 1 second the weight that child can eat. What we do, people? 500 we divide by 10. G by S. Here we get 50 grams per second. What do you mean by that, people? In 1 second, the number of grams that child has eaten. It is called as, people, rate. Rate means this is expressed as a fraction. This 50 means it has 1 at the denominator. Rate means when this denominator is 1, what is the value of the numerator? In this case, the denominator is 1 second. In 1 second, the number of grams eaten by the child. That is called as rate of eating rice. So therefore, here also, people, this gradient is what? Rate of change of y. Rate of change of y with respect to x. Why do we use the with respect to x? The denominator variable is x. Here, denominator variable is time, with respect to time. So therefore, this gradient we can introduce as how, people, the rate of change of y with respect to x. If we further explain that one, if this denominator x changes by 1 unit, what is the corresponding change in y? That change of y can be, people, either increasing or decreasing. Okay, that is called as the gradient. So therefore, in this case, according to this graph, you can see when this x increases, y also increasing. Here, when we are here, our x value is this. The corresponding y value is this height. When we increase our x from here to here, our new y value is not the earlier this. Now it is this y increased. Then in this case, you can see as x increases, y also increasing. Therefore, in this case, y changes by increasing its value. And if I consider the graph in the other way around, for example, this way, consider. Right. Now, suppose we are here people. The corresponding y value is this now for our first x value. Now we increase our x value to another value like this. This is our new x value. The corresponding y value you can see here. This. Then early y value here, now that has decreased here up to this. If the line is like this, people, you can see as x increases, y decreases and y changes by decreasing its initial value. Then you can see the gradient positive mean, people. Its meaning is as x increases by 1 unit, y increases by a particular value. That particular value is the rate. When the gradient is negative, you can see as x increases, y decreases. As x increases by 1 unit, the decrease of y is defined to be the rate or the gradient. Anyway, remember this gradient mean, people, rate of change of y with respect to x. Rate means when x changes by 1 unit, the corresponding change in y. Right. Now the next thing is this. If I consider the standard equation of the straight line, it is the y equals mx plus c. It is the y equals mx plus c. Right. When I consider the standard equation of the straight line, people, y equals mx plus c, in it this m and c both are constants. Right. If I differentiate these both sides with respect to x, you know dy by dx is equal to this m is a constant, people. Derivative of x with respect to x is 1 plus derivative of c, since it is a constant, alone 0. Then here we get dy by dx is equal to m. M means the gradient. Therefore, people, what is the practical meaning of dy by dx? The practical meaning of dy by dx means by the differential coefficient of first derivative, people, we get what? The gradient function of a given graph. The graph can be straight line, quadratic graph, or any other curve. Understood? Okay. So therefore, so far, by finding dy by dx, people, really, what have we found? That is really, people, the gradient function for a given equation of a graph. Gradient function. That means, in other words, since the gradient has the meaning rate of change of y with respect to x, we have found that rate of change of y function with respect to x. Right? That's the one we have found. Okay. So therefore, dy by dx is nothing but rate of change of y with respect to x. Dy by dx positive mean, people, gradient positive. Gradient positive means the line like this, right? Line like this. That means rate of change of y with respect to x is positive. That means as x increases, y increases. Dy by dx negative mean, people, the gradient negative. Gradient negative means the line should be like this. Then you can see as x increases, then in that case y decreases. This is the key thing in this application of derivative, people, right? You have to very clearly understand this concept, then the application of derivative is very easy and interesting one. Okay. Yeah. The next thing here we should know, people, when we consider not only the straight lines, there are many shapes for curves. There are many shapes for curves. Now, when I consider simply a curve like this, right? Y equals x squared plus 1. See? The curve is a minimum curve like this. We have drawn this in quadratic equation lesson. And if I consider another one like this, y equals sine theta, y equals sine theta, the curve is like this. People, when you move along this kind of curves, not like a straight line, you can see from point to point, the rate of change of y changes, right? Now, for example, when we consider this kind of straight line, when you move along this line like this, we can see when you move from A to B, we have moved to right and we have moved to up, right? The distance moved to right is people this. The distance moved to upward is people this. Okay. Now here, if I consider on this line between these 2 points, when I move from here to here, you can see right and upward this way. Okay. If I move somewhere here like that, people, from here to here, you can see what? Right, this upward, this very small value. Then can you understand in this case, when the graph is not a straight line, like this, a curve, you can see the rate of change of y when we move along the graph changes. Place to place, that changes, right? Gradient changes. Dy by dx changes. Gradient means dy by dx, no? That changes. Then once you differentiate this one, you can very clearly understand when you differentiate this one, people, we get dy by dx, you know, this is 2x, derivative of 1 is 0, we get dy by dx is 2x. So this, what is this 2x? People, we said what? From point to point, the gradient changing. The gradient changing. The variation of that change, and if we try to explain that variation by an equation of this gradient, it can be written as 2x. So therefore, the gradient function only, people, by dy by dx we get. Okay, the other thing is this. Now, for example, if I take this graph, y equals sine theta, on this graph, suppose we are given a point P. At this point P, when we pass the point P, people, there is a particular gradient. When we need to measure the gradient at the point P, what we do is, people, at the point P to this curve, to this graph, we construct a tangent. Tangent means a line, people. Tangent means a line. That line touches this graph at this point like this. This is a tangent line. We measure the gradient of this tangent line by measuring this angle. You can do that. If this angle is beta, its tan value is the gradient of this tangent line. People, the gradient of this curve at the point P is then taken as the gradient of this tangent line. That is how we define the gradient of a curve at a given point. The gradient of that curve at that given point is considered as the gradient of the tangent drawn to that curve at that point. Its gradient only we consider as the gradient of the curve. Okay, right. So then these are the initial thing you have to understand before going to this application of derivatives. Okay, then people will take down brief note and then we'll come to the next part, right? Yeah. Write down like this. Write down like this. Consider the straight line given by its standard form, given by its standard form, y equals mx plus c, y equals mx plus c, y equals mx plus c, where m called as the gradient, c intercept. Right. We define this gradient like this. First, we'll draw a diagram like this. X, y. This is the origin now. This is a line with the equation y equals mx plus c. Suppose this angle here we have theta. Then gradient we define how, people? M is the notation, gradient m defined as tan theta. Here the height, this is the intercept. Right. First draw this diagram and we'll write one sentence. Right. Write down like this. The gradient of a straight line, the gradient of a straight line, the gradient of a straight line is defined as the tan value is defined as the tan value is defined as a tan value of the angle the line makes with the positive x-axis, the line makes with the positive x-axis in anticlockwise. In anticlockwise sense. Right, people, next. The intercept is the distance from the origin to the point where the line cuts the y-axis, Right. Then write down subheading straight lines with positive and negative gradients. 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 Positive gradient people like this. Just like this people. Theta angle is less than 90, greater than 0. Okay. Negative gradient line like this. This is the theta now. Gradient is tan theta here. Theta less than 5, greater than 90. M equals tan theta. Or what people? What other way of measuring the gradient of this? When you put minus sign to the right, then angle this we have to take, right? Or minus tan alpha. When you put minus sign, if you know the gradient is negative people, that gradient can be obtained how? M equals, since we know the gradient is negative, minus sign we put, and then you have to take tan of the left angle. Tan. Okay, right. Right. So now you can see if alpha increases, that means this line comes like this, alpha increases, then this tan alpha increases, but since it has negative sign before it, value increasing having negative sign before that, then overall value is people we say decreasing, right? We say decreasing, right? Write on that too. Right. Okay. Now you can see here. Next one, we'll write. Write down the meaning of the gradient. The meaning of the gradient. Right, people, you know what is the meaning of the gradient? It gives us rate of change of y with respect to x. What do you mean by that, people? As x changes by 1 unit. Changes means either increasing by 1 unit of x and or decreasing by 1 unit of x. Anyway, as x changes by 1 unit, the corresponding change in y is the rate. Usually when we consider the way of changing this x as increasing, as x increases by 1 unit, the corresponding change in y is called as the rate of change of y with respect to x. Right. Write down. The gradient gives the rate of change of y, simple y, with respect to x. Simple y with respect to x. Rate of change of y with respect to x. That is as simple x changes by 1 unit, as simple x changes by 1 unit, the corresponding change in y, the corresponding change in y is called as the rate of change of y with respect to x, with respect to x, with respect to x. Right. Then you can write, therefore, m equals the rate of change of y with respect to, we write like this, with respect to x. Write down like this. Now consider y equals mx plus c. Now consider y equals mx plus c. Now people, we differentiate this both sides with respect to x. Write down, differentiate in with respect to x. What do you get there, people? dy by dx, m derivative of x with respect to x is, people, 1 plus that of c is 0. And we get dy by dx equals m. dy by dx equals m, people. dy by dx equals m. That means what? dy by dx mean it gives the gradient. That means dy by dx gives rate of change of y with respect to x. Okay, write down like this. That is by dy by dx, by dy by dx, we get the gradient function, and therefore it gives the rate of change of y with respect to x, the rate of change of y with respect to x, with respect to x. With respect to x, people. Right, so then you can again draw another two small diagrams like this. X here, y here, origin over here. Right, here you can very clearly see here, gradient is positive, obvious. Gradient means dy by dx. dy by dx is positive. In this case, people, you know the variation of x and y. When we move on the x-axis in the direction x increases, you can see while we move to the right along the x-axis, the y also increasing. That means the dy by dx positive case we can identify as x increases, y increases like this. Okay. This one, x, y, this way. You know, obviously, gradient in this case negative. Therefore, dy by dx negative. In this case, you can see as when you move in the direction x increasing along the x-axis, people, you can see as we move to the right along the x-axis, the height decreases. As x increases, y decreases. Y decreases. Right now. Now write down another subheading like this. Gradient, subheading write down, the gradient of a curve, the gradient of a curve at a given point, on the curve, at a given point on the curve. Well, I am going to take my curve with the shape like this. This is a curve. Suppose we have a point P on this curve. At the point P of the curve, if we need the gradient, people, first thing we have to construct a tangent to this curve at the point P. That means we have to draw a line. That line touches the curve at the point P. You know, in physics, in practicals, of course, you know, after drawing the curves, we have to construct tangents to measure the gradient. In that case, I think in physics, you have learned how to construct a tangent line to a curve at a given point on the curve. Okay, so here also we construct that tangent line to the point, to the curve at the point P like this, this way. Okay, if this angle is theta now, people, you can find the gradient of this tangent line L. The gradient of this tangent line L only, people, we accept as the gradient of the curve at that point P. Okay, right? This is a tangent line. Tangent line. Its gradient of L. Tan theta. Therefore, gradient of the curve at point P. Therefore, the gradient. Therefore, the gradient of the curve at P equals tan theta. Right, people, did we write something? We wrote only the heading. Thereafter, we drew this diagram only, no? And we wrote like this. Did we write anything? No. Have we? Did we write something like this? The gradient of a curve at a given point on the curve is considered as the gradient of the tangent line constructed at that point on the curve. No. Right. Then after writing everything, people, drawing everything and writing like this, we'll write one sentence. Write down like this. Write down. The gradient of a curve, the gradient of a curve, the gradient of a curve at a given point on the curve, at a given point on the curve, is considered as the gradient, is considered as the gradient, is considered as the gradient of the tangent line, of the tangent line, of the tangent line drawn to the curve at that point, at that point. Right. We'll come to next part. As a note, we'll take down this. Note. Let S displacement V velocity T time. Then people, what is ds upon dt? Rate of change of displacement with respect to time t. What is that? In 1 second, the change in displacement. What is that, people? That is velocity. ds by dt is velocity. Velocity v. Number 1. Number 2, dv by dt. dv by dt. What are these, people? Rate of change of velocity relative to time. That means in 1 second time interval, change in velocity given as acceleration. No, people, somebody answering acceleration. In 1 second time interval, this gives us what, people? 1 second time interval, change in velocity, that is rate. Because this velocity, it can change in 2 directions. No, how? Increasing the velocity, it can change in 1 second, or in that 1 second, velocity can change by decreasing it. Are both accelerations? No. This is, people, acceleration, no retardation. If this dv by dt ratio is positive value, you can see gradient positive, no? Of what? Of the velocity and time graph. Here time, this is velocity. If this dv by dt means it's gradient, no? Then the curve should be like this vt graph. Gradient is positive. Then you can see when we have this kind of velocity time graph, as the time elapses, what can we say? Velocity increases. Increasing rate of velocity is acceleration. So therefore, this is acceleration, no retardation. Acceleration or retardation. If dv by dt greater than 0, positive, it is acceleration. If dv by dt people negative, dv by dt means gradient, no, gradient negative means this, no people, then this is v, this is t, no. You can see when we move in the increasing direction of time people, you can see velocity decreases. That is the retardation. So therefore dv by dt negative, it is a retardation. It is a retardation. Okay, right. Then the first type of questions under this lesson, the first type of questions under this lesson, write down first type. Write down questions relating to or questions related, questions related rate of change, questions related rate of change. And we will take your tutorial. Take your tutorial. In the tutorial people, under the application, page number 20, take question number 77 as the first question. Question number 77. Right. First read the question, people. Try to understand this question. Right. Let's see this. Question gives like this: a particle moves along a curve 6y equals x cubed plus 2. Find the points on the curve at which the y coordinate is changing 8 times as fast as the x coordinate. 8 times as fast as the x coordinate. People, what is this really? A particle. A particle. Right. Suppose that curve is this. Its equation given by 6y equals x cubed plus 2. Well, you can see when we move somewhere from here to here, you can see though we move to right, hardly any what rise of y, hardly any what motion upward direction. But not like there. When we move from somewhere here to here, you can see when we move, when you draw horizontal line here, vertical line here, you can see when we move this horizontal distance to right, there's a particular rise of vertical too. That says people, on this curve when we move from place to place, right, the gradient changes. Rate of change of y changes. Now asking what people? Find the points on the curve at which the y coordinate is changing 8 times as fast as the x coordinate. What does it mean by that, people? What do you mean by that? Y coordinate is changing 8 times as fast as the x coordinate. That is real, people, the rate of change of y with respect to x. Rate of change of y with respect to x should be 8. That means as x changes by 1 unit, y should change by 8 units. That is nothing but, people, dy by dx is the rate of change of y with respect to x. Dy by dx should be 8. Dy by dx should be 8. Right? Then we need to find what, people? The points on this curve at which the dy by dx is 8. For this, what we do, people, we differentiate this function of this graph. And then we get 6 times y equals x cube plus 2. We have differentiated this 6 dy by dx. Let's keep the 6 as same. Dy by dx. X cube is 3x squared 2. When you differentiate 0 because it is a constant alone. Then you can consider cancel down this one and this. People, now you can write dy by dx is x squared by 2. You can see the variation of the gradient is a function of x. That means what? Is a function of x means what? When the x coordinate of the point changes, accordingly, what? The gradient changes. The rate of change of y with respect to x changes. It is not a constant. We can see constant gradient only for a straight line. For the rest graph, people, the gradient changes as x changes, x coordinate changes, or the point changes, in other words, because as x changes, what happens? The point changes, no? Right. Now, what we need to find is, people, the points on the graph at which the dy by dx is 8. So then what we do is we equate this dy by dx to 8. Then x squared by 2 is the dy by dx, but dy by dx we know as 8. This is 8. By this you can use the cross multiplication. It is 16. X comes as plus or minus 4. There are two x values. One is plus 4, other one is minus 4. Okay. Then there are 2 points on the graph satisfying the required condition. Dy by dx is 8. People, when we consider a point has 2 coordinates. Now, for example, if you ask to find on the xy plane the point which has the x coordinate 1. Now, you are asked to mark a point on this xy plane, x coordinate is 1. Can you mark that, people? No. To mark a point on the xy plane, we should have its x coordinate as well as y coordinate. Then, to give this point, people, x coordinate we found already. Y coordinate we have to find. Then what we do is, people, taking this x equals 4 and substituting that way here, we find this y. Then what do you get? 6 times y. X to the power 3 means 4 to the power 3 plus 2. This is 64, no? 4 to the power 3. 64 plus 2 is 66. And this is 6y. Y is 11. Then one point is 4, 11. 4, 11. Okay. Secondly, x equals minus 4. 6y. Put minus 4 to the power 3 plus 2. Minus 4 to the power 3 means, people, minus 64. Plus 2 means minus 62. That we have divided by y. Then we get, people, minus 31 by 3. Then the other point is minus 4 minus 31 by 3. So these are the 2 points on this given graph. The gradient is 8, or y changes 8 times as fast as x changes. Okay, right. Right. As a second question, people will take 79 part 2. Question number 79, second part. Take that question number 79 part 2 as the next question. Right. Read the question and try to understand that. (79) part 2. If the volume of an expanding cube, if the volume of an expanding cube is increasing at the rate of 4 cubic centimeters per second, Then how fast is the surface area increasing when the volume of the cube is 8 centimeters? 8, sorry, not the volume. Yeah, 8 cubic centimeters. When the volume of the cube is 8 cubic centimeters. Right now, suppose this is the cube. This way. It's our cube. In this cube, people, you know, length, breadth, and height being equal. I'll take this as x, this also x, this also x. Now, people, this cube is expanding. Once it expands, people, the volume is increasing. Right. Once the volume increases, the length, breadth, and height must increase. Once these three, length, breadth, and height increase, people, the surface area increases. Then now we are asked to find the rate of increase in surface area when the volume of this expanding cube reaches to 8 cubic centimeters, right? Volume is increasing, people. Once this volume is increasing, one occasion. Now, while this volume is increasing, people, you know, the surface area also increasing. There are 6 surfaces for this now. This side, other side, this side, top and the bottom. There are 6 sides. The total area of all these 6 sides, right, increasing as volume increases. Then, while the volume increases like this, one occasion the volume of the expanding cube reaches to what? 8 cubic centimeters. Even that instant, the surface area is increasing. At that instant, there is a particular way of increasing the surface area now. If we maintain without change that rate, that speed of increasing the surface area over 1 second, then we can see particular increment of area during that second. That is called as, people, the rate of increase in surface area at the volume of the expanding cube is 8 cubic centimeters. So a very practical question, right? So then I'm going to write, people, the volume. I'm going to take the volume as V, right? Then what is the volume, people? Volume is length, breadth, and height. Volume is x cube, right? Volume is x cube, right? And, people, volume is increasing, right, at the rate 4 cubic centimeters. Volume is increasing at the rate 4 cubic centimeters per second. If the volume of expanding cube is increasing at the rate of 4 cubic centimeters per second. What is this, people? Rate of increase in the volume. How to write? Rate of increase in volume with respect to time t mean, people, dV by dt. dV by dt. What is this? Rate of change of volume with respect to time t. In this case, this change occurs of this volume in the increasing direction because it is expanding. Therefore, rate of increase in volume with respect to time t is this dV by dt. It is the one given as, people, 4 cubic centimeters per second. It is 4 cm3 s minus 1 dV by dt. right? Like this. We know these two. Okay, now we can write the surface area. Surface area. Surface area is A. Surface area is A, people. Right, there are 6 surfaces. One surface is of area x squared. Length into breadth, no? There are 6 such surfaces, then 6x squared. Right. Now what we need to find, people, rate of how fast is the surface area. How fast? How fast means, people, rate in 1 second. In 1 second, what is the increase in the area when the volume of the cube is 8? People, the rate of increase in the area we need to find. Rate of increase in the area, people, dA by dt. dA by dt. We need to find dA by dt when the volume of the cube is 8 cubic centimeters. This is what we need to find. People, volume 8 mean this is 8, no? When this V is 8, 8 equals x cube mean 2 to the power 3 only 8, no? Then x takes 2. Then volume 8 means the same thing we can write, x is 2. Then really what we need to find is, people, we need to find dA by dt at x equals 2 centimeters. This is what, in other words, we need to find. Correct, no? Yeah. Now let's see how to find that. I'm going to take this V equals x cube. I'm going to differentiating with respect to t. T means time. Then when you differentiate V with respect to time, people, to the left hand side we get dV by dt. On the right hand side we get d upon dt x cube, like this. D upon dt x cube. People, now here how to differentiate this? Here we have x. We have differentiated that with respect to t. If we have here t cube, that can be differentiated with respect to t as 3t squared. But here we have x cube. Then here we have to apply chain rule, people. I'll explain the way of getting this, and thereafter in the latter case, people, we straight away take that. I write here d upon dx and x cube times, then dx upon dt is the way of writing chain rule. Dx and this dx you can cancel down. Then dx cube upon dt, this same thing coming. People, what is this? Derivative of x cube with respect to x. It is 3x squared. 3x squared into dx upon dt. Then, people, here and after, don't write this step. We'll write directly this answer from this. How to write, people? First, whatever this letter here we have, we differentiate this power 3. Then that is 3 comes before x, 3 minus 1. 3x squared, this is coming. That should be multiplied by the derivative of this letter now. Letter is x. When you differentiate that with respect to x, people, the derivative is written as dx upon dt. What is this dx upon dt? Dx upon dt is what, people? Rate of increasing a side of the cube. Okay, that means in 1 second, what is the increment of the length of a side of the cube? That is dx upon dt. But people, we know this dv by dt here given as 4. Then I can put that, people, for this dv by dt, this 4. Then I can subject this dx upon dt, taking this 3x squared to this dx upon dt. We can write 4 upon 3x squared. We'll keep this we need. dx upon dt equals 4 upon 3x squared. Right. Now I am coming to this a equals 6x squared. A equals 6x squared. Then I can write differentiating this a with respect to t people, dA by dt. 6 I have to keep like that. This x square we have differentiated, that is 2x, and now x should be differentiated with respect to time t dx upon dt, right? The step without writing this, I directly got that. And then here we get people what? dA by dt is 12 times x times dx by dt. This dx by dt, people, is 4 upon 3x squared. 12x dx upon dt, 4 divided by 3x squared. Okay, dx upon dt is 4 divided by 3x squared. Then here, x and this we can cancel down. 3 and this 12 we can cancel down. 4 and 4 we get 16 upon x. Okay. Then you can see dA by dt is inversely proportional to what x. That what can say, people? As the length of a side of the cube is increasing, the rate of increase in the surface area, people, decreasing. Can you understand that? As the length increases of a side of the cube, rate of increase in the surface area is decreasing. It doesn't say, people, surface area is decreasing. It is to say, people, if we take one example, consider this. We have a conical vessel like this, and we open a tap which pours water constant rate. Constant rate means, people, in 1 second the same volume of water pouring into this conical vessel by this tap. Now, see, you can see, people, with the time, time elapses, the water level is increasing. People, from the start to end, if you very carefully watch the rise of the water level, what kind of thing you can see, people? Initially, water level is rapidly increasing, but with the time, water level is increasing, but in 1 second, the increment of water level is less compared to early stage of this. Water level is increasing. Increasing rate is, people, gradually decreasing. In the early stage, in 1 second, water level increased by 10 centimeters. But in the latter, with the time elapses, people, water level is still increasing but the increasing rate as the time elapses. Early stage, in 1 second, 10 centimeters rise. Second, water level increasing, but 9 centimeters only in the second depth increases. Third second, water level increases by 8 centimeters. Water level is increasing, increasing rate is decreasing. Remember that. It doesn't say the water level decreases. Okay, so like that here. With the time, sides x length increases. It is where, people? At the denominator. As x increases, the ratio is decreasing. That means what? It is equal to dA by dt, no? The rate of increase in the surface area decreasing means that. Now we need what, people? This dA by dt at x equals 2. So then we can put here for this x2. Therefore, dA by dt at x equals 2. We write it like this. Right? It is 16 upon 2. 16 upon 2. It is what people? 8 square centimeters per second. 8 square centimeters per second. 8 square centimeters per second. So therefore, in this way, the expanding cube increases its volume, people. When its volume reaches to 8 cubic centimeters, its surface area is increasing at the rate 8 square centimeters per second. Right? So this is how we work out that question. Right? Yeah. Right. Complete the question. And people take next one. As the next question, number 81. Read number 81. As the next question, number 81. Read number 81. Okay, people, now we'll come to the question this. Yeah, question number, I told you to start the question number 81. Number 81, right. Sand is being poured from a pipe at the rate of 8. The pond is on the ground in such a way that the height of the pond is always 1/4 of the rate. How? But this case, sand is being poured from a pipe. Right, people. This way, we have a pipe, right? Sand is falling from the pipe at the constant rate. At the constant rate mean, people, in 1 second, the volume, the sand volume adding to the ground, always in every second being a fixed value. So practically, when we set a pipe to pour this sand onto the ground, you can see gradually the falling sand forms a cone. Naturally, you can see this. Then, suppose this is the ground, the falling sand forms a cone like this. Right. We are given people this base radius mean, when we consider a cone, people, the cone has a circle like this as its base. It's a circle, people. The circle has a center. Circle has a center. Circle has center like this. This circle therefore has a radius. This is called as a base radius. Now here, we can join. This is a cone. This is called as a vertex. This vertex and this center of the base, when we join by a line, This line is called as the axis of the cone. And if this axis is perpendicular to the base, such cone is called as the right cone. Right cone. The length of the axis, these people, is called as the height of the cone. Height of the cone. Okay. Right. So now we are given the falling sand forms a sand cone. Its height is always, people, 1/4 of the base radius. 1/4 of the base radius. That means if the base radius is r, height is r divided by 4. Right. I'm going to take, people, the height as h of the sand cone. Then the base radius should be, people, 4h. 4h. Right? People, you know, if the height, if we take as h here, the volume of this kind of right circular cone, volume is given by 1/3 pi r squared h. This is the formula. 1/3 pi r squared h. Now you can write the volume of this cone like this. Volume of the cone. V, we can write, people, V equals 1/3 pi r squared, 4h squared, into, people, height is h. This is the volume of the cone. This is the volume of the cone. And then we can simplify this. What do you get? V equals 4 squared is 16 pi divided by 3. 4 squared is, people, 16 pi divided by 3. Here we get h squared and here h cube coming. This is volume. People, now in this case you can very clearly see the pipe pours sand in every second a volume 8 cubic centimeters. Due to that, what happens? The volume of the sand cone increases. In 1 second, the volume of sand cone increases by what, people? 8 cubic centimeters, because the volume, the pipe, of course, adds to the cone. In 1 second is the rate of increase in of the volume of the sand cone. So therefore, the volume of the sand cone changes or increases, in other words, in 1 second by 8 cubic centimeters. That means, people, dV by dt, right? dV by dt, dV by dt is given 8 cubic centimeters. Okay, it is 8 cubic centimeters, no? Right, this is 8. Cm3 is -1 like this. Now, what is asking, people? How fast is the height of the sand cone increasing when the height is 6 centimeters? People, now, when this continues in this way, in every second, volume of the sand cone increasing by 8 cubic centimeters. That occasion, what happens? As the time elapses, volume is increasing, meantime height is increasing. People, in this way, one occasion, the height of the sand cone reaches to 6 centimeters. Even at that moment, the height is increasing. If we, people, keep what the rate, the speed of increase in the height when the height reaches to 6 centimeters during 1 second with the same speed, in that 1 second, particular increment of height you can see. That height only, people, that increment only we see the rate of increase in the height when the height is at 6 centimeters. That means, people, what we need to find is we need to find this dH upon dt. dH upon dt value, what is this? Rate of change of this height. In this case, the change of the height occurs by increasing it. dH by dt. We need this dH by dt at h equals 6 centimeters. This is the one we need to find, people. This is the one we need to find. Right? Okay. Now let's see how to take this. Okay, right. Now you can draw this diagram. This is important because the vertex axis, those things you should understand. The volume of this cone is given by 1/3 pi r squared h. That's also important. We'll draw this, right? Yeah. Now what I take is, people, I take this and I differentiate with respect to time t on both sides, right? Yeah. We need finally to find this. We finally to find these people, right? V equals 16 pi by 3 h cube. I am going to differentiate this with respect to time t, dv by dt. This is a constant, people, 16 pi by 3. Now we have to differentiate this. When differentiate this, people, first we have to differentiate, we have to start from this power 3. 3 h squared. And now you should multiply that by the derivative of h with respect to time t. That is nothing but dH by dt. No, we apply their chain rule, but I am not going to show that application of chain rule by using another separate step. We'll write like this. Okay, right. Now this dv by dt is, people, 8. Substitute for this, dv by dt 8. This 3 and this 3 you can cancel down. 16 pi h squared dH by dt coming. This 8 and this 16 you can cancel down by 8. We get 2 there. Then we get 1 upon 2 pi. 2 pi h squared we take toward left hand side, denominator like this. It is equal to, people, dH upon dt. dH upon dt. Now we need, people, that dH upon dt value at h equals 6 centimeters. So therefore, we can subject by this dH upon dt. 1 upon 2 pi. We need the value of this at h equals 6 centimeters. Right? So then we get, it is 1 upon 2 pi 6 squared. 6 squared is 36 into 2, 72. 1 upon 72 pi. Right? This pi is 22 upon 7, people. Pi is 22 upon 7. You can simplify that. And thereby you get the rate. So this units come in as centimeters per second. Right? Centimeters per second. Centimeters per second, right? Right. This is how we do the questions related rate of change. Right. Now we'll come to the next part. That is the right. Another important part is the maxima and minima. Maxima and minimum. Right. Right. Now write down subheading as simple like this. Write down maxima and minima. We move to the second type of application under this, application of derivatives. Right. Write down maximum and minimum. Maximum and minimum. Right. Now people will see a minimum graph like this. You can't see that, no? This is the y-axis, this is the x-axis. Suppose like this, a minimum graph, people. We drew this kind of graph in quadratic equation. Listen. Yeah. Well, you can see here the vertex or the lowest point. The lowest point on the graph when we consider. This point only having the least y value compared to other points on the graph. See here, the height from the x-axis to other points greater than this height. Therefore, this point is called as, people, minimum point. Minimum point. Okay. Now, if we consider, keep, of course, constructing tangents while moving along the curve like this. Why? We construct tangents to this curve. We construct tangents to this curve. See here, somewhere here when we construct tangent, the tangent line is this. Right? Somewhere here, the tangent line is this. Somewhere here, the tangent line is this. You can see the tangent, of course, gradually turns towards the x-axis. At this lowest point, people, when we keep drawing that tangent become parallel to x-axis this way. Thereafter, if we draw the tangents on the right of this minimum point, again the tangents being like this. You know, on the left of this point, all the tangents, they have the gradient negative. On the right hand side, gradient positive. Gradient positive. Exactly at the minimum point, people, the dy by dx gradient 0, because the line is horizontal, then that does not make any angle with the positive x-axis. Angle is 0, tan 0 is 0, therefore the gradient is 0. This way, people, gradient 0 mean gradient means what, people? Rate of change of y, no? Rate of change of y. Then gradient 0 means rate of change of y is 0. That means though x increases or decreases, in other words, x changes, y doesn't change. Y doesn't change. Doesn't change means, people, is stationary. What is stationary? Y is stationary. Where? At this point. Why? Dy by dx, the gradient 0. Gradient means rate of what? Change in this y. It is a dy by dx. It is 0 means y doesn't change. Y is stationary. So therefore, people, this point is called as stationary point. Stationary point. Stationary point. And the other thing is, people, when we walk along this graph in the direction x increases, when you walk along this way in the direction x increases like this, people, you can see after reaching the lowest point, furthermore, when we move along the graph in the direction x increases, you can see this is the point. We were, of course, pointing this way, moving and reaching to this point, and then if we continue further the motion, our direction change soon after this point. So therefore, this point is called as turning point. Our direction changed to our opposite direction at that point. So therefore, the points at which dy by dx 0 are called as stationary points or turning points. Turning points. Understand? People, this way, a stationary point or turning point can occur in another two ways. When we consider a maximum graph like this. Here, the highest point, again, when we construct a tangent line, that will be parallel to x-axis. On the left of this point, when we construct here, gradient positive. On the right of this point, when we construct tangent lines, gradient negative. See here. Here on the left of this, gradient dy by dx positive. At this point, dy by dx 0. Here, dy by dx negative. This is another stationary point, maximum point, right? So therefore, people, this point is called as minimum point or simply minima. This is called as maximum point, maxima. People, another kind of points we can see. Those points, of course, have the property this. Suppose we have a minimum point at the vertex. Suppose a maximum point occurs of a maximum graph like this. The vertices of the minimum graph and maximum graph being now, people, coincident points. Now, when we construct tangent, dy by dx is, people, 0. Now, if we erase this portion of this graph and this portion of this graph, people, at this point dy by dx is 0. On the left of this, on the left of the portion has negative gradient. On the right of the portion has a negative gradient. This is neither maxima nor minima, but there's a stationary point that is called as, people, point of inflection. Point of inflection. Point of inflection. Another kind of point of inflection you can see, it is, of course, the erase in other portions like this. This is another kind of point of inflection. But the real definition of the point of inflection is not this. This is what? A point of inflection with a stationary point. With a stationary point. Okay, so therefore, remember, stationary points means the points on a graph where the dy by dx is 0, the gradient 0. The stationary point can occur in three ways: at a minimum point, at a maximum point, or at a point of inflection. The stationary point can occur. The stationary points are termed as, people, turning points. Turning points. Okay, right. And then, people, under this maxima and minima, we'll write another subheading as stationary point or turning point. Write down stationary point or turning point. Stationary point, within bracket write down turning point. stationary point, in bracket, turning point. Write down. Write down. A point on a curve, a point on a curve, a point on a curve at which dy by dx equals 0. dy by dx equals 0. Within bracket, gradient 0. Gradient 0. Gradient 0. Gradient 0. Cross bracket. Is called as a stationary point. It's called as a stationary point. Stationary point within bracket or turning point. Right. Write down. Start from new line. A stationary point. A stationary point. A stationary point can occur on a graph basically in three ways. Basically in three ways. Right. First one, write down. Minimum point or minima. First one, minimum point. Simply we call it as minima, like this. Right. We'll draw like this, people. Right. Suppose this point is corresponding to x equals a. Draw this way line. Draw this way line. Draw this way line. Here the gradient negative. Here the gradient is positive. Exactly at this point, gradient 0. At x equals a gradient 0. Okay. And then the condition required to occur a minima or minimum point at a point dy by dx must be 0. On the left of it, dy by dx negative. On the right of it, dy by dx positive. If then, of course, at that point x equals a, at that point where dy by dx becomes 0, there is a minimum point or minima, right? Okay. So therefore, we can say number 1, dy by dx x less than a negative. Number 2, dy by dx x equals a equals 0. Number 3, dy by dx x greater than a positive. Right, people? If these 3 occur one after other, people, then these 3 conditions required for a minimum point at the point x equals a, right? Then we can write there exists a minima at x equals a. Right. Second one, people, maximum point, maxima, number 2. Maxima. Right. We'll do that too, people. X, Y, origin, this way. X equals a, at x equals a, the dy by dx equals 0. Before that, on the left of that point, dy by dx positive. On the right of that point, dy by dx negative. Right. Right? We'll come there too, people. Dy by dx, x less than a, on the left of a, positive. Dy by dx exactly at a, 0. Dy by dx x greater than a, negative. These 3 together create a maximum point at x equals a, or maximum. There exists a maxima at x equals a. But here, third one, point of inflection. Write down, third one. There are 2 forms of occurring point of inflection. Point of inflection. Point of inflection. Right, there are 2 types, people. We'll draw. Here on either side, the gradient has the same sign. Here dy by dx 0, dy by dx negative. Before that point also dy by dx negative. Let this point be x equals, say, x coordinate of this point, x coordinate is a, y axis, this is x axis, right? On either side the same gradient negative, then this is one kind of point of inflection, right? If we write dy by dx x less than a negative, dy by dx x equals a 0, dy by dx x greater than a, also negative. This says at x equals a, there exists what people point of inflection. There are exits. A point of inflection at x equals a. The other possibility, the point of inflection occurring in the other way. The other one is this. Dy by dx positive, this side also the same sign positive, y-axis and x-axis. Then this is also another kind of point of inflection, right? Having a stationary point. 1. Dy by dx x less than a region positive, dy by dx at x equals a 0, dy by dx x greater than a, also positive. Then these three together, people, they exist. A point of inflection at x equals a. These are the 4 possibilities where a station point can occur. Right. And therefore, people at a stationary point or turning point, dy by dx is 0. Dy by dx is 0. Then, given that an equation of a curve asking you to find the stationary point or the turning points with their nature. Nature means, people, whether it is a maxima or minima or point of inflection. Then people using this first derivative, variation of the sign of first derivative, using that fact, you can find the x and y coordinates at the stationary points or turning points, and by finding the signs of dy by dx, whether it is a maxima or minima or point of inflection. That way, when we determine a stationary point, that is called as, by using the first derivative, finding the stationary points. We'll do, people, one example. Then there is another test for that. That is a second derivative test. We'll come to second derivative test after this example. Okay, then put a star mark and then write like this. Then write down. Therefore, at a stationary point, the dy by dx equals 0. The dy by dx equals 0. Dy by dx equals 0. Right. We'll come to one example. People, are you tired? Write down, people, the question. Find the stationary points and their nature of the curve with the equation x cube divided by 3 minus 3x squared by 2 plus 2x plus 1. By using the first derivative. Right. This is the, people, the equation of the curve. Then to find the stationary points, at stationary points dy by dx 0, no? We'll first differentiate this. Right. Write down this one and then write differentiating with respect to x. We can write dy by dx equals this third 3, we can write as 1/3. X cube we can write as 3x squared. This 3 by 2 is a constant, people. X squared derivative is 2x. 2x derivative is 2. 1 is 0. This and this you can cancel down. This and this you can cancel down. Dy by dx we get x squared minus 3x plus 2. People, we can factorize this. We can factorize this. Dy by dx is equal to x minus 1, x minus 2. Right. Now we know at the stationary points dy by dx become 0, people. Right. Then you can write at the stationary points dy by dx equals 0. Then x minus 1 times x minus 2 equals 0. Equate this to 0. this way. X is 1 or X is 2. People, this X equals 1 and X equals 2 give us X coordinates on the graph where the gradient 0, because we got them by equating dy by dx to 0. Then they are at this point x equals 1 and x equals 2, people. There are stationary points, but so far we don't know the nature, whether it's a maxima, minima, or point of inflection. We don't know. That we need to find. Before that, people, we have to find out the y coordinate for each point. X coordinate is known, right? So now x equals 1 we can put where? Here. X equals 1, put where? Here, and find y. Y equals 1 cubed by 3 minus 3 into 1 squared by 2, 2 into 1 plus 1. Y is 1/3 minus 3 by 2, and here 3 people. Now we can simplify this. We can write here 6, 2 minus 3, and 18 here. (20 minus 3 is 17). 17 by 6. Therefore, one point is x equals 1. 1, 17 by 6. Secondly, put x equals 2. X equals 2. Y 2 to the power 3 by 8. 3 by 2, 2 squared. 2 into 2 plus 1. Here we can cancel down this and this. 8 by 3. Here 4 and 1, 5. Here minus 6. Then minus 1. Y is 5 by 3. Then next point is 2, 5 by 3. The 2 points, therefore, we have now with the coordinates. First point is 1, 17 upon 6. Second one, 2, 5 by 3, like this. Okay. Right, now people, there are 2 stationary points, but we don't know their nature, whether they are maxima, minima, or point of inflection. Right. Now, to find these people, we have to use the sign of the gradient or the dy by dx. For this, we prepare people a small table. We prepare a small table. This way you have to, of course, follow even at the examination. For that table, you get marks, right? Then this is the table, people, right? Then I erase this. Okay. Now we have the x values at which dy by dx 0 as 1 and 2 people. Then on the number line, we mark this 1 and 2 in order. 1 and 2. This is 1. People, you can very clearly see, once you mark on the number line this 1 and 2, this 1 and 2, divide this number line into 3 regions. The region on the left of 1, between 1 and 2, on the right of 2. Accordingly, now, creating regions or range, we create this way a table. This region is x less than 1 region. This region is x less than 2 but greater than 1. Very easily you can remember. This region is x greater than 2. Now each interval we are going to find the sign of dy by dx. Here we write in columns the sign of dy by dx. Right. To find the sign of dy by dx, people, this is what we do. Here we have the expression for dy by dx. Here we have the expression for dy by dx. In that expression, people, we substitute taking values from each region. Now, in this region, take any value you like. In this region, people, you know, 0 lies. 0 is on the left of 1. Right. Once I put 0 here and here, 0 minus 1, this is minus 1. 0 minus 2, this is minus 2. Minus 1 into minus 2. Minus minus plus. 1 into is 2. Plus 2. This sign only we need. And in this interval, between 1 and 2, put any value for x. 1.5 say. 1.5 minus 1 is positive. 1.5 minus 2 is minus. Plus and minus make minus. Right. X greater than 2. Any value for x greater than 2, like 5. 5 minus 1 positive. 5 minus 2 positive. Positive into positive is positive, people. This way. Now, positive gradient line in this interval, if we draw, it should be like this. Exactly at x equals 1, we know gradient 0, the line is horizontal. After that, in this interval, it is negative. Positive gradient, 0 gradient, negative gradient. People, obviously here, then that should be of the shape this, therefore it is a maxima. So therefore, at x equals 1, y 17 upon 6 coming, at that point, there is a maxima. Similarly here in this interval, negative gradient, exactly at 2, 0 gradient, in this interval, positive gradient, then this is the shape. This x equals 2, it is a minimum shape, minima. Therefore, this is maxima, and this is minima. Right? Then we can write at 1, 17 upon 6, a maxima. And 2, 5 by 3, a minimum. This way we can do that. Right. Okay, people. Next part is local maxima and local minima. Write down next subheading like this. Local maxima and local minima. Local maxima and local minima. But people now will consider this way, a graph. Suppose we have a graph like this. A graph we have like this. This way. People, you can very clearly understand this is the point corresponding to the maxima. This is the point corresponding to the maxima. This is the point corresponding to minima. This is also minima. People, this is the minima. This is minima, maxima, maxima. People, when we consider this one, it is called as the maxima. This y coordinate of this point is the greatest compared to y coordinates of the points of the neighboring points on either side of this point. Okay, when we consider very close points on the right and left of this point on the curve and find its y values, those y values, people, are less than this. Then, people, this point is called as local maxima. People, it is having maximum y value. That is why it is called as a maxima. Its y value is greatest compared to neighboring points on either side of that point. But overall maximum value of the y coordinate of the graph is not this. Here you can see the graph is going this way toward plus infinity. So therefore, when we consider somewhere here a point, its y value is of course greater than this y value of that maximum point. So therefore, people, such points are called as local maxima. Similarly, here this point and this point are called as local minima. Why? Those points have minimum y values compared to y values of the neighboring points on either sides of that 2 points. But overall minimum value of the whole graph, if we consider, people, this way, the graph is running to negative infinity. These y values are, people, really negative. Negative values are anyway less than the positive values. So therefore, people, that way we identify local maxima and local minima. You know, people, now when we consider in a village also, in a school, say, the headmaster is the first. He is the powerful person. That is only for that school. For any other school, any student, don't care. So therefore, his power is only inside that particular school. So therefore, he is a local principal. He is the powerful person in that school only, like that. When we compare on either side of these points on the left and right, compared to the y values of those points, this is the what, people, highest y value. Therefore, this is called as local maxima. Right? Understand, people? That is how we just identify local maxima and local minima. Right? So then we'll mark this one as local maxima. Here, local minima. Right. Right. First draw this one and we'll write one sentence. People, it seems taking another like 10 minutes or 15 minutes to complete the things. We'll see. Write like this. Write down like this. Write down. If the y value right, people, tell me what I said. Write down, people. If the y value of a point, if the y value of a point is the greatest of the y values of the neighboring points of the y values of the neighboring points on either side of that point, then that point is called as a local maxima, Right on. In a similar way, we can identify a local minima, Right. People, now we'll come to the last part. Second derivative test for maxima and minima. Write down. Second derivative test for maxima and minima. Second derivative test for maxima and minima. Right. Second derivative test for maxima and minima. Right. Now I am going to consider one minimum graph like this. See, this is our minimum graph. The minimum occurs at x equals a. This is x-axis, this is y-axis. Now, people, I am going to sketch the graph of dy by dx against x. This way. Right, you can very clearly see, people, the gradient is dy by dx, is the negative dy by dx axis. You know, when we have a graph like this, when we keep drawing the tangents like this, you can see this angle here, this angle, people decreasing. Gradient negative, angle decreasing. Angle decreasing means, people, tan decreasing. Tan decreasing means real number is decreasing with value. We have, people, minus sign before. Having minus sign before, if the some real numbers getting decreased, people, overall minus value now increasing. So therefore, I am going to sketch dy by dx. Somewhere here we measure the gradient. Somewhere here we measure the gradient. Somewhere here we measure the gradient. Okay? Gradient and corresponding x value. Those points I mark. Then if I consider somewhere here the gradient, x value is somewhere here, gradient is negative. The point comes somewhere here like this. We come to here, gradient negative, but earlier like -3, now like -2. There's an increment. Therefore, somewhere here the point. Like that, people, when you come to this x equals a, at x equals a, the gradient of this is 0, no? Then at x equals a, exactly the gradient is 0. Then when you move to right of x equals a, people, gradient is positive. Since the angle increasing, the gradient increasing with positive value like this. Okay. Therefore, when we construct a graph by joining these people, this kind of graph coming. What is this graph? This graph is the graph which explains clearly the variation of the gradient of this graph. People, you can very clearly understand, to find the gradient of this graph, it is dy by dx now. We have to differentiate this y. Then to find the gradient of this graph, this one again we have to differentiate with respect to x. When you differentiate this dy by dx with respect to x, people, we get the second derivative of y with respect to x, d2y upon dx2. Then you can see this is at x equals a. Is at x equals a. At x equals a, if I draw a tangent to this graph, people, that tangent you can very clearly understand having a positive gradient here. This has the positive gradient. The gradient of this curve means the gradient of this tangent. Gradient of the curve means, people, second derivative. So therefore, it is d2 y by dx2 at x equals a. You can see here it is positive here. So therefore, the second derivative test is this. If we have minima at a particular x value, at that x value, second derivative takes the positive sign. That's the second derivative test, right? Then if I consider maximum graph in the same way, people, we can construct the dy by dx graph. Suppose we have a maximum graph like this. At x equals a, suppose we have the maximum. On the left of this a, we have positive gradients of the tangents. Like this. Now I am going to construct what the dy by dx graph. Right? Now at x equals a, dy by dx 0. Before this x equals a, on the left of a, dy by dx is positive, but as we move along the graph towards this highest point, the dy by dx decreasing towards 0. Then it is like this, people. This way points we get. And then after this point, that dy by dx become negative like this. Then this is that, people, x equals a. At x equals a, in this case, when we construct a tangent, you can see this tangent has what? Negative gradient. The gradient of this tangent means second derivative, because here, people, this axis is now dy by dx. This is x. The gradient of this curve means we have to differentiate this. Similarly, to get the gradient of this one, we have to differentiate this with respect to x. Then we get a second derivative. You can see gradient is negative. So therefore, here the gradient is negative. Gradient is negative. d2 y upon dx2 at x equals a, negative. So therefore, people, by this we identify when there is a maximum point or maxima at a given x value, definitely there the second derivative is negative, people. Second derivative is negative. Okay, right. First draw this one and we'll then write one sentence. That's the end of today's lesson. People, my y value is wrong in the earlier case. If it is wrong, correct that one. Right. Now we can write. By the above graphs, we can easily conclude. We can easily conclude at a minima, the second derivative takes positive sign and at the maxima the second derivative takes negative sign. Right. Right, people, then this is the today lesson. Next week we can come to the maxima and minima questions, right? Then there are some more questions we have to discuss, right?